Example 6. A rectangular cake dish is made by cutting out squares from the corners of a 25 centimeter by 40 centimeter rectangle tin plate and then folding the metal to form the container. What size squares must be cut out to produce the cake dish of maximum volume? So we have a diagram here. We're going to start labeling it. So it's 25 centimeters by 40 centimeters. These are all squares, which means each of those little corners has the same dimensions. We could call them x by x. So call that x, call that x. This whole thing is 40. This whole thing is 25, but we could call that x and this x, which means that this portion in here could be 25 subtract 2x, and this portion in here could be 40 subtract 2x. Because when we transfer that and cut those pieces out and get rid of them and fold it up, then we are actually going to have this dimension 40 minus 2x, this dimension 25 minus 2x, and this dimension will be x. What size squares must be cut out to produce the cake dish of maximum volume? Okay, so we're looking at volume. Volume is length times width times height. So in this case, 40 minus 2x multiplied by 25 minus 2x multiplied by x. When we expand that out fully, I won't go through all the steps, but we get 4x cubed minus 130x squared plus 1000x. All right, so step 1 was the diagram. Step 2 is the formula. We need a formula. Okay, and we've got v equals, and we only have one variable there. Step 3, the derivative. So dv dx is 12x squared minus 260x plus 1000. Set that derivative equal to 0 and solve. This is a quadratic. We're going to factor out a 4. If we divide both sides by 4 now, 0 divided by 4 is still 0, so we have this. Split that middle term, and the numbers are, oh sorry, this should be a 3x here, 3x squared. Subtract 15x, subtract 50x plus 250. And so on and so on. Just want to make sure you get the right middle term there. So x minus 5 equals 0, so x equals 5, or 3x minus 50 equals 0, x equals 50 over 3. So roughly 16.7. Okay, since x is a measurement, it has to be bigger than 0. We need to determine what our interval is here. And I guess we should have done that up in this step. Our interval. So can x be any value whatsoever? Okay, so could it be infinity? Well, no, it couldn't. Okay, because we only have 25 units to take x away from here. Okay, we have 40 units to take x away from here, but 25 smaller. So in other words, 25 minus 2x has to be greater than 0. Okay, that dimension here has to be greater than 0. So let's see, negative 2x is less than negative 25. Solving inequalities, divide through by negative 1, we have to change the sign. So x is less than 12 and a half. Okay, but it has to be bigger than 0. So therefore our interval is between 0 and 12.5. Okay, so we're only considering those places. Now, if we take that into consideration, this value is too big. Okay, so it's not one of our critical values. So we're only looking at x is 5. Step 4, for a restricted domain, the max or min may occur either when the derivative is 0, or at an endpoint, or at a point where the derivative is not defined. Okay, so show using the sign diagram test, or the second derivative test, or the graphical test that you have a max or min. Step 4. Let's try the second derivative test. That's the one that they've used in the example also. The second derivative is, we have to figure it out here based on this, 24x subtract 260. So second derivative test, putting the 5 in there, we get negative 140. Okay, this is a negative number, which means that it's going down, which means that we have a local maximum. Okay, so we are okay. We do have a local maximum. And so we have our answer then. The maximum volume is obtained when x equals 5, which means 5 centimeters cut from each side. Okay, so each of this is 5 centimeters, this is 5 centimeters. So step 5, what size squares must be cut out to produce the cake? Okay, step 5, the squares must be 5 centimeters by 5 centimeters to produce the maximum volume.